Welcome to this tutorial on limits of functions at a point. In this tutorial we're going to look at what it means for a function f of x to tend to a limit L at a particular point x0. So we're going to look at the formal definition of the limit, and we'll explain exactly what the definition means using some diagrams, and we'll look at some examples of how to prove limits. So let's start off with the formal definition of the limit of a function at a point, and we will talk about exactly what this means, so try not to be put off by the sight of it. Now, part of the problem with this definition is that it involves these strange symbols epsilon and delta, and the first time you see this definition it's not clear exactly what these quantities, epsilon and delta, are supposed to represent. So in fact, before we talk about the formal definition, let's start off with something a bit simpler. We're going to have a look at a diagram to illustrate the idea of limits of functions. So here's a graph of a function, and suppose this function is f of x equals 2 to the power x, and say this is our scale on the x-axis, so this red dotted line is at x equals 2, and we're going to look at what happens to the function, in other words the curve in blue, when x approaches a value of 2. So you can think about x approaching 2 from the left-hand side on the x-axis, or from the right-hand side, and this is why we sometimes talk about left-hand and right-hand limits, because when x is approaching a particular value, it could be approaching from either direction. In this particular example, it doesn't matter whether you think about x approaching 2 from the left or from the right, the limit is still going to be the same. So the question is, what happens to the function as x approaches 2? Well, obviously, since our function is 2 to the power x, which is a continuous function, so it doesn't have any gaps or jumps in it, the function approaches a value of 2 to the power 2, which is 4. And because the function f of x approaches 4 as x approaches 2, we say that this limit as x approaches 2 is equal to 4. Now let's consider a slightly different function. This time the function is defined differently depending on the value of x. So if x is not equal to 2, the function is still 2 to the power x, but if x equals 2, the function takes a value of 5 instead of 4. So on the graph, if we look at the point x equals 2, we have a hollow circle here, and we have a filled-in circle up here at the value of 5 on the vertical scale. So this indicates that f of 2 equals 5. So now if we draw a line through 4 on the vertical axis, we're going to ask ourselves the same question as before: what value does the function approach as x approaches 2? So now that we've changed the function, the question is it still going to approach 4, or is it going to approach a different value? Well, the answer is, as x approaches 2, these arrows are still pointing in the same direction, and the function still approaches 4. It doesn't approach 5. So even after we changed the function, the limit as x approaches 2 is still 4, despite the fact that f of 2 equals 5. So the point is that changing the value of the function at x equals 2 actually makes no difference at all to the limit as x approaches 2. So in general, when we're trying to find the limit as x approaches a particular value x0, we have to see what value the function approaches as x approaches x0. And the important point is, if x is approaching x0, that means x is not equal to x0, and therefore the value of the function at x0, in other words f of x0, has no effect on the limit as x approaches x0. So in the example we just looked at, it wouldn't have made any difference if f of 2 had been 4, 5, 40, 50, 700 million, or any other number you can think of. In fact, the function could even have been undefined at x equals 2, and we would still have been able to say that the limit as x approached 2 was equal to 4. So now let's go back to the formal definition again. We say that the limit of f of x as x approaches x0 is equal to some number L if for all positive numbers epsilon it's possible to find a positive number delta such that we're guaranteed to have the modulus of f of x minus L smaller than epsilon whenever the modulus of x minus x0 is strictly between 0 and delta. That's what the definition says, and here's an informal version of it using words. So basically what the definition is saying is that we can make f of x as close as we like to L by making x close enough to x0 without being equal to x0. So if you compare these two definitions, you might wonder, are they really saying the same thing? Well, yes they are, because if you look at this part of the formal definition, this is talking about making the distance between f of x and L, in other words the modulus of f of x minus L, smaller than epsilon, no matter how small epsilon is. So that's saying that we can make f of x as close as we like to L. And over here, this part of the definition is saying the distance between x and x0, in other words the modulus of x minus x0, needs to be strictly between 0 and delta. So that's saying that we need x to be close enough to x0. It's just a question of working out how close x needs to be to x0. In other words, how small we need delta to be. And generally, the value of delta actually depends on epsilon, because the smaller epsilon is, the smaller we need delta to be, and we're going to illustrate that in a moment. And this is why we sometimes write delta of epsilon with the epsilon in brackets, because delta is actually a function of epsilon. In other words, delta depends on epsilon. Now we're going to illustrate the epsilon and delta definition just to show exactly what it means. So suppose we have a function which looks like this. It doesn't really matter what the function is, we're just using this as an illustration. And somewhere on the horizontal axis we have x0, which is a fixed value of x, and somewhere on the vertical axis we have L. So as x approaches x0, meanwhile the function is approaching a value of L, and we want to prove that the limit as x approaches x0 is equal to L. So now let's draw two red horizontal lines, and the top red line is at the value of L plus epsilon on the vertical scale, and the bottom red line is at L minus epsilon on the vertical scale. So here we're thinking of epsilon as being a fixed small number. Obviously if epsilon was smaller, the lines would be closer together, and if epsilon was larger, the lines would be further apart. And the space in between the two red lines we're going to call the red zone. Now if you look at where the function, in other words the blue curve, enters the red zone, it enters the red zone at this point here, and then it leaves the red zone at this point here. And now we're going to draw two vertical lines at these 2 points, and because of the way we've drawn these lines, we can say that if the value of x on the horizontal axis is in between here and here, that means the value of the function will be in between L minus epsilon and L plus epsilon. In other words, the distance of the function from the limit will be smaller than epsilon. So the point of the red zone which we've drawn is that if the function is in the red zone, that means its distance from the limit is smaller than epsilon. Now imagine we draw a small open symmetric interval around x0 on the x-axis. You can see that if we make the interval small enough so that it's contained between the two green lines, that means we can say that if x is inside the interval, then the value of the function will be between L minus epsilon and L plus epsilon, because clearly it will be inside the red zone. So if we say that our interval goes from x0 minus delta to x0 plus delta, you can see the idea is that if we make the interval small enough, in other words if we make delta small enough, then we know that whenever x is inside the interval, that means the function is within a distance of epsilon from the limit L. So what we're saying is that provided we make the interval small enough, we can say that if x is in the interval from x0 minus delta to x0 plus delta, not including the point x0, because we want to think about what happens as x approaches x0, rather than what happens when x equals x0, then f of x is in between L minus epsilon and L plus epsilon. Or in other words, if we write that another way, we can say that if the modulus of x minus x0 is strictly between 0 and delta, then the modulus of f of x minus L will be smaller than epsilon. These two statements are mathematically equivalent, so they're exactly the same. Now just before we move on, imagine what happens if epsilon gets smaller. If epsilon gets smaller, then obviously these two red lines will get pushed closer together. And over here, these two green lines will also get pushed closer together, because remember, the green lines show where the function enters the red zone and where it leaves the red zone. So that's going to mean that the interval from x0 minus delta to x0 plus delta needs to become even smaller in order to fit between the two green lines. So the point is that if epsilon gets smaller, we need delta to get smaller as well. And in the second part of this video, we'll look at some examples of how to prove limits.